So at the end of lecture on Tuesday, we briefly just talked about these four types of reactions. Four types of reactions: decomposition, where something falls apart; synthesis or combination, where multiple things come together into a bigger thing; single displacement, where one single thing displaces another thing, so you just basically kick out one partner for another; and then double displacement, where things switch partners. Okay, we're going to take a little bit closer look at each of them. Here's decomposition. Remember, a complicated thing falls apart into two or more less complicated things. One example is ammonium chloride. It decomposes into ammonia gas and HCl. If you see one thing on the left in the reactants, it has to be a decomposition. There's nothing else it can do except fall apart. Okay. This is mercury oxide. Okay. It decomposes and forms mercury metal and oxygen gas. The gas you can't see because it's oxygen gas. It's clear. And then mercury now looks like what you expect mercury to look like. Liquid metal, silver metal. Okay. Here, it's in compound form. Looks like that, and then it breaks apart into your mercury metal and your oxygen gas.
It shows the O2 is negative, or it's O2 negative.
Yeah, so when it's here, it's in the oxide, the anion form.
Okay.
So it's oxygen with a 2- charge. Here, it's an O2 form, which has no charge. It's not an ion anymore.
That's released by E.
Yeah. So here's an example. Okay. It says predict the products and balance the equation for this decomposition. And it gives it to us in name. Platinum chloride, platinum 4 chloride decomposes to its elements. Okay. What is the formula? Platinum 4 chloride. Platinum is PT. Leave it at that. Platinum is PT. Then we have chloride, which is a Cl. What's the subscript on the PT? Nothing. It's 1. The charge on chloride is 1, so it's a 1 here. What's the subscript on the Cl? 4. It tells us it's platinum 4, so the charge on platinum is 4, so the subscript on chloride is 4. So that is our reactant. Yields, and it says decomposes into its elements. So what do you think those are?
Platinum and chlorine.
Platinum and chlorine. So I'm going to say this is solid, this is solid. Solid gives platinum, and I'll tell you platinum is a solid, plus chlorine gas. Is that correct?
Yes.
Hmm? Right. Before we even start balancing, is this written correctly?
Yeah.
I'll tell you no. The answer is no.
Cl twice, Cl2 twice.
Cl2. Chlorine is one of those diatomic ones. So it's Cl2. Now we can balance it. What do we have? This one's easy to balance. What do we have to do? We can put a coefficient of 2 on the Cl2, so now we have 4 chlorines on each side. Platinum started off balanced, 1 on each side. This is a synthesis combination. Again, we have simple things coming together to make a more complicated thing. Zinc metal, chlorine gas to make zinc chloride, the ionic compound. It's sort of basically the opposite of what we did here. Here we took an ionic compound and broke it into elements. Here we're taking elements, putting them together into an ionic compound. Yeah?
How did you know between solid and gas on that?
I just knew. You would have to be told that.
Okay.
You wouldn't know. With combination, you can add two single things together to make a kind of a double. You can add a single to a double to make a triple. It doesn't matter. If you're taking multiple things and combining them into a more complicated thing, it's a synthesis. Okay? Generally, there's only going to be one thing on the right-hand side in the product. If there's only one product, it has to be a synthesis. You can also take two compounds and combine it into one bigger compound. Generally, these synthesis reactions are going to make ionic compounds. Metal reacts with a non-metal to make an ionic compound. You can have a non-metal that reacts with another non-metal. You're not going to see that as often. But keep in mind, you can have either one happening. Okay? And like we saw, you can take two compounds, combine them together into a bigger compound. So this is an example of a synthesis. Here, this is carbon monoxide. If you add oxygen gas to it, you get CO2. We have two things on the left, one more complicated thing on the right. These were two molecular compounds or elements combined together. There's no metal involved here. But you took two things, made one. By definition, that's a synthesis. Yes. Here's an example. We're supposed to predict the product and balance the equation. So what do you think that's going to make?
Aluminum bromide.
Yes. So we have aluminum solid plus bromine gas yields AlBr. What's the subscript on the Al?
Nothing.
Well, nothing. There's one. What's the subscript on the Br?
Two.
No. Al, we don't have a big periodic table in here, but Al is a 3. Aluminum is a 3, with AlBr 3. I'm going to say that's a solid. Now we have to balance it. Actually, I missed something. Yes. It's a Br2. Okay. Now how do we balance it? Yes. The first thing I would do is make the right side an even number, because they're always going to come in pairs over here. So now we have 6 bromines over here. You can put a 3 here, and now we have 6.
Now you
You'll
can
put
two
a
on the
two
little
on the
cells.
L.
Yes. Makes sense? Single displacement and double displacement are going to get a little bit harder. Okay? The synthesis and decomposition, there aren't many options of what it can do. Single displacement, A is going to displace C to become partner with D. So you're going to end up with AD, and C is by itself. Okay? The question becomes, why did A kick out C rather than D? Why did A want to form a compound with D rather than forming a compound with C? And we're going to see how that works. In a single displacement, you're going to have a compound and you're going to have an element, with no exceptions. You're going to have a compound and an element. The element is going to displace one of the other elements in the compound to make a new compound, and the one that got displaced is going to turn into the element. So here, this is our element, this is our compound. A displaced C to make a new compound, AD, and C is now off by itself as an element. This is a reaction with copper solid, it's just a copper wire, put into a solution of silver nitrate, which is a clear solution. They react. The copper displaces silver from the silver nitrate to make copper nitrate and silver metal. When we look at this, what's on this, forming on this copper wire is silver metal. And blue solution is copper nitrate. Silver nitrate was clear, copper nitrate is blue. So we know that the copper came from the wire into the solution, and the silver came out of the solution onto the wire. We're going to do this at least once, but I think twice in lab. Okay. Yeah.
Is there still a little bit of copper wire underneath there, or did it change
Yes.
all silver?
No. So what happens is once you get a coating of silver, then the copper inside doesn't touch the solution anymore, and so it stops.
So you can do that as many times until there's no more silver in the fluid, right?
Right. So if you wanted, you could take that out, take this brushed silver off, put it back in, and it would react until there was no more silver in solution. People actually, some of the old film processing solutions had silver in them, so people would go to photo processing places, take their waste solution, go home and do something like this to get the silver out of it and sell it. It's kind of like nowadays where people get the grease and make biodiesel. They're throwing it away anyways. If you're willing to put the work in, go for it.
My macroeconomics teacher does
It's
that.
actually worth
Yeah.
it.
Oh,
I
yeah.
have a friend that does it.
Yeah.
His car smells like French fry.
So here is some examples of single displacement reactions. Okay. Here, aluminum is replacing the iron to make iron metal, liquid metal, and this aluminum oxide. Okay, I think this is a reaction we looked at before with this really strong hot reaction. There's another one, iron replacing copper to make iron oxide and copper metal. This is asking us what happens to the charge on the metal that does the displacing, meaning the one that displaces something else. What is the charge on the metal here? It's not an ion. It's just a metal. So what's the charge on something that's not an ion? 0. It doesn't have a charge, right? When it forms the compound, what is the charge on the aluminum? Now it's an ionic compound. Positive what? Aluminum is 3. Aluminum is 3 plus. So the metals go from 0 to a positive charge. That's what's going to happen in these reactions. Here is the same reaction, looking at it the other way. If we put copper metal in silver nitrate solution, we get this going on. So there's silver on the copper in the solution. In this case, it's not as blue as before, but trust me, that one is more blue than that one. If we put silver metal in copper nitrate, the reaction does not go the other way. This looks exactly like that. Nothing happened. What this is the nitrate wants to be with the copper. If it's already with the copper, it'll stay with it. If it has to switch to get to the copper, it will switch. This slide's out of order sometimes. This is just a few slides down. Based on the reactions that we've seen, we can point out that copper displaces silver. We saw that. That means that copper is more active than silver. We saw that iron will displace copper, so iron is more active than copper, and aluminum is more active than iron. But we have to have a way to predict whether this reaction is going to happen rather than setting it up and seeing. We have this activity series. It's in your, like the back of the front of your book. It's also on that cheat sheet for the quizzes and the final. Okay? What you do is the further up you are, the more active it is. the more reactive it is. If something that's up high will displace something that's down low. So, will magnesium displace hydrogen?
Yes.
Yes. There's magnesium, there is hydrogen. Magnesium will shove hydrogen out of the way. Will aluminum displace hydrogen? Yes. There's aluminum, there's hydrogen. Aluminum is higher. Will iron displace zinc?
No.
There's zinc. No. There's iron, there's zinc. Zinc is higher. The one that's higher wants to be in the compound. Okay? The higher you are, the more power you have, you can be in the compound. Okay? If you're the more powerful one and you're not in the compound, you can grab the other person, throw them out of the way, and join the compound.
Sounds like a zombie movie.
I guess. I don't really see it. So, here we're going to mix calcium metal with water. And we're going to predict whether it's going to react. If it does, we have to write the reaction. Okay. So we have calcium metal plus liquid water. We have to predict whether there's going to be a reaction. So, what do you need to look at on that activity series to figure out if there's going to be a reaction? If there was a reaction, what would displace what?
Calcium displaces hydrogen.
Calcium would displace hydrogen. So what do you need to look up there to figure out if that's going to happen? Yes. So you need to figure out if calcium will displace hydrogen.
Is it above hydrogen?
Right. Is calcium above hydrogen?
Yes.
Yes. There's calcium, there's hydrogen. Calcium is more reactive, meaning it's stronger, it'll get its way, it wants to be with the oxygen. So we're going to switch the calcium for the water. So we end up with calcium oxide plus hydrogen. That's a solid. That's a gas. Yes.
How do you know which element in the compound your other element wants to replace?
It's going to replace the metal. In this case,
Okay.
the hydrogen is acting like a metal. If you see something like oxygen, that's clearly a non-metal.
Right.
It's not going to displace it. Also, if it's not up there, if it's not on that list, you're not going to use it in a single displacement reaction.
Okay.
It can be this sort of bystander, the thing that just,
Yeah.
the other partner that doesn't get a say in anything. But those are the only elements you're going to be dealing with. Yeah. So, is this balanced? Yes. So that one's done. That's how you predict and write a single displacement reaction. Is there another one? No. Hmm? Oh,
When water breaks down, doesn't it drop off the
you're right. So it doesn't make calcium oxide. It makes calcium hydroxide plus H2O. Now we're definitely not balanced.
Why did it make it OH? Yeah. So then all you need is a 2, not H2O.
This one's more complicated than you would have. You would have one that they would just switch. Rather than having this H2O, water is, as strange as it sounds, water is about the most complicated molecule there is. Okay. So you would have, say you had calcium plus NaCl. That one's a lot simpler. Will calcium displace sodium?
Yeah.
Yes. Yes. Calcium is just above sodium. So now it's very easy to see what you're going to switch and make, right? So you get calcium chloride plus sodium. What if we had
But that's not balanced. You have two after the chlorine, so we can't put a two for this one.
2 there and 2 there? What if you had zinc metal plus KCl? It won't. So what if you had this? What you would write is no reaction. Okay. So single displacement. You first have to figure out if there is a reaction, and if there is, what is it? If there isn't, you write no reaction.
Why is it no reaction?
Because zinc is there, potassium is there. Potassium is the more reactive one. The more reactive one wants to be in the compound, and it already
It's already
is.
in the compound. Alright.
But isn't it also reactive if, because it says react with cold water, so don't you need the cold water to react it? To give H2 right there, it says react with cold water to give H2.
This is a reaction for if you're just putting in water. I would, if I were you, I would ignore everything to the right.
Okay.
Just look at this. You don't need this water to make it happen. What that's saying is, if you put potassium in cold water, it will react. If you put lead in cold water, it won't work. Zinc in cold water won't work, but zinc in steam will react. Okay. That's that water thing. It's really complicated. In our double displacements, we're going to start with 2 of these compounds and see if they want to switch. Okay. There's 3 types of double displacement reactions. There are precipitation reactions, there are gas formation reactions, and there are acid-base neutralization reactions. We're going to talk about precipitation and gas. Acid-base has its own whole chapter later in the semester. Okay. Precipitation and gas formation reactions are going to be very, very similar. The only difference is one of your products here is going to be a solid, and this one of your products, is going to be a gas. The similarity between them is in both cases, you're going to take 2 aqueous solutions, mix them together, and then you're going to get either a solid or a gas. So something is going to leave your solution. Either it's going to form a solid and sink, or it's going to form a gas and bubble out. In this one, we're mixing barium chloride and sodium sulfate. When we do that, they switch partners. We now have barium sulfate and sodium chloride. Sodium chloride is still soluble, right? So it's still dissolved. Barium sulfate is not soluble in water. So it forms a solid, and we could say it precipitates out. So this is a precipitation reaction. It's making a precipitate. Which of these ions in these, so what ions are in our reactants? There are 4 of them. What ions are in this compound? Barium and chloride. What ions are in this compound? Sodium and sulfate. So you have 4 ions to start with: barium, chloride, sodium, sulfate. Okay? They are all in solution. They're all floating around independently. When you do a reaction, you now have, one of the things you made is NaCl. NaCl dissolves in water. So the sodium and the chloride are still floating around independent. Which ions would you say underwent a chemical change? The barium and the sulfate. They're over here, they were ions. Over here, they're in a compound. The sodium and the chloride are ions over here, and they're ions over here. We have to be able to predict what is going to form a solid. And just like the activity series, we have a solubility table. Okay? And so what you do is you swap the partners, see what two compounds you might make, look at this table, and figure out if one of them is not soluble in water. Okay? So this table has two columns, a soluble column and insoluble column. Start on the left, look at your metal. If you have a sodium, potassium, ammonium, it is a solid. It's soluble. No questions asked, no matter what it's bound to. No matter what the anion is, it's soluble. If your anion is a nitrate or an acetate, no questions asked, the whole thing is soluble. If your anions are chloride, bromide, or iodide, they're soluble unless they're paired with silver, mercury, or lead. You do the same thing just like this. Sulfates, silver, and copper are soluble unless they're paired with these. Okay? And going the other way, carbonates, phosphates, hydroxides, and sulfides are insoluble unless they're bound to an ammonium or something in group 1. Group 1 is all the way to the left, that first column. You will have a solubility table like this on that cheat sheet. You don't need to memorize it, you just need to know how to use it. Okay, so here's an example. We're going to mix lead nitrate and potassium iodide. We have to first predict whether they're going to react, and if they are, what are we going to make? If we were to switch partners, what compounds would we now have? If we just switched,
So the ions, lead, iodine,
yes,
potassium,
we'd have lead
and iodine.
and iodine, which would be PbI2, and then we would have potassium nitrate. Before I even try to balance this, I'm first going to see if there's a reaction. If there's no reaction, we don't have to balance it because it's not a reaction. So we look at these two things on here and see if one of them is insoluble. Find lead iodide. Is lead iodide soluble?
No.
No. So iodide is soluble unless it is with lead. So lead iodide is a solid. Is potassium nitrate soluble?
Yes.
Yeah. All nitrates are soluble. So this is aqueous. So we do have a reaction. So we do have to balance it. So what do I need to do? 2 nitrates on the left. So I have to put 2 here to balance the nitrates. But now my potassiums are out of balance. So I have 2 potassiums, 1 over here, so I'll put 2 here, and then also at the same time balanced my iodine. How many people have done the homework and tried balancing anything? Anybody? Okay. So if you were asked this on a quiz or an exam, this is the type of answer you're looking to have. Here's another one. we're mixing cadmium 2 nitrate, this, and sodium sulfide, that. She got an orange precipitate that she knows is cadmium orange. It says identify the precipitate and write a balanced chemical equation for the reaction she carried out. So we have, I'm not going to bother writing the reactants this time. So those are our reactants. There's something, we don't even need to look at the solubility chart to know which compound is insoluble. Right?
Nitrate. All nitrates are.
Right. So, well, if you remember the solubility chart, you can do that. Do it that way. All nitrates are soluble. If we switched partners here, what would we make?
Cadmium sulfide and
Cadmium sulfide and sodium nitrate, right? The question tells us that what she made is called cadmium orange. So cadmium orange probably is not the name for sodium nitrate, right? It's probably the name for the cadmium sulfide. So we know there is a reaction. It tells us a precipitate form. So there is a reaction. So we know our products are the cadmium sulfide and sodium nitrate. Cadmium, yeah. So then you would have to then go balance it. But the hard part is writing the products. If you want, there's the how they did it. Here's another one. Well, the answer's already up there. No, it's not. Okay. So this one's telling us that a precipitate forms. We're mixing these two things. What are the products? We switch our partners, what do we have?
barium chloride.
We have barium chromate. The CrO4, that's not one I told you to memorize. Barium chromate, CrO4, plus, what's the other thing we make?
Sodium chloride.
Yeah. And also sodium chloride. So those are the two things we made. We have to figure out which one is the precipitate. Which one of those do you think is insoluble on that chart?
The broken chlorine.
Right. The barium chromate is clearly sodium chloride is soluble. So this is a solid. This is still aqueous. Double displacement reactions with gas formation work exactly the same, except one of your products, instead of being a solid, is going to be a gas. Okay? And it's generally going to be pretty obvious which one is the gas. You're either going to form bicarbonate, like that, or you are going to form something like H2 or O2 or N2 or Cl2, something that's very clearly a gas. So in this case, we mixed calcium carbonate and hydrochloric acid. You get calcium chloride and that. That actually will break down into carbon dioxide and water, which is why that acts like a gas. My guess is you won't see one where you form that. Okay? We will come back to this when we start talking about buffers, because this keeps us alive. Okay? For these, you'll probably form something like probably H2 or O2 would be my guess. So here is that breaking down into that. This is what happens with acid rain and limestone. Limestone has calcium carbonate in it, acid reacts with it, and it forms that gas and it goes away. Like I said, the last double displacement reaction is acid-base. Don't worry about it now. Basically, acids react with bases. You know that when you react acids with bases, you always, always, always get salt and water. A salt. And we'll talk about later what I mean by a salt. We're going to skip the acid-base stuff. Okay. So mark on there, we skipped the acid-base stuff. There is a fifth type of reaction. It doesn't very neatly fit into one of the four categories, and that's a combustion reaction. In a combustion reaction, you react something with oxygen with a whole bunch of heat in a flame, and you get products. If what you're burning is a carbon compound, because carbon and hydrogen, you're always going to get CO2 in water. No exceptions. If you burned C8H15, you would get CO2 in water. If you burned CH2, you would get CO2 in water. The only thing that would change is how you balance the equation. Okay? Combustion reaction, something with carbon reacting with oxygen in the flame gives you CO2 and water. No exceptions. And that's what that's saying. So here, this is really big. C8H18, two of those react with 25 oxygens to give 16 CO2s and 18 waters. I'm glad you didn't have to balance that one. But it was really big, CO2 and water. Doesn't matter. So let's give names to these. Is this synthesis, decomposition, single or double replacement? Decomposition. Complicated things become less complicated. Which one is this? Synthesis. What's that? Single. What's that one? Double. Okay. Here is the same type of idea, but in chemical reaction note and formulas type notation. What type is this? Synthesis. Two things become one. What is this? Double replacement. It just switched partners. You can see that. What is this? Decomposition. One thing becomes two. And what is that? Single replacement. You started with a compound and an element, and the element kicked the lead out, and so it is now with the chlorine. Anybody feel like, given an equation like that, they could not classify it? Okay. Predicting the products is a whole nother issue. I just want to make sure that you can classify them. Okay. You do need to be able to predict the products, but if you can't classify them, you're going to be really stuck. You won't have any idea what the product is supposed to be. Let's try to classify them using pictures. What do you think this is? There's a precipitate forming here. So what kind of reaction is it? Double replacement. Precipitation reactions are double replacements. We had one solution here, one solution up here. We mix them, we get a solid. What is this?
Double or combustion?
So this one's tricky. It's burning, right? So you could say it's combustion, but that is, I can tell by looking at this, this is magnesium metal. This is what we did in lab, okay? Magnesium metal is not a carbon compound. When we reacted magnesium metal in the flame with the oxygen, we made magnesium oxide. So in this picture, we have magnesium metal and oxygen gas in the air. We make magnesium oxide. What kind of reaction is it? Synthesis. Okay. This is a pH meter. pH has to do with acids and bases. We didn't talk about that. Okay. So that is a beaker with a solution in the bottom and a chunk of metal in it giving off, my guess is iodine or bromine gas. What do you think that was?
Decomposition.
I would say it was probably single. You started with a metal bar in a solution. That's what we had for our single displacements. Okay. I don't know what the heck that is. But the metal that was in the bar is displacing the metal that was in the solution, and you're getting some sort of gas that comes off. What about this one? What would you call that? Double? This one? This one's combustion. It's flame, it's burning, and this is natural gas. Natural gas is methane, which is CH4. This is a carbon compound burning. It's combustion. I have no idea what that is. What would you say this one is?
Alka-Seltzer.
Yeah, so you drop something in the water, you're making a gas. Which type of reaction made gas? Double displacement. This is a double displacement where one of the things you made is a gas. What's this? Single. Same exact reaction. This is exactly what you're going to do in lab. You're going to put an iron nail into copper nitrate. And so you're getting the copper forming on the iron nail, and you're forming an iron nitrate solution, which is clear. So at this point, there is still some blue in the water. You didn't react completely. If you let it keep going, eventually the water would turn completely clear. Let's try and just classify them this way. What would you call that? There's little white ones on here. Synthesis. You have two different things. Here you have all one thing. What would you call this? Decomposition. This is all one thing, became multiple things. Here? Single. The blue one is displacing one of the green ones. What about this one? Double. The blue is now with the white, and the green is now with the red. It just switched. How about this one? Synthesis. You have nitrogen and hydrogen gas. Now we have NH3, ammonia. How about this one? Synthesis. We have a solid, we have a gas. They're combining into an ionic compound. What? No, that's not right. That's not right. Decomposition would be going backwards. How about this one? This one's a single. Here, you had the white ones floating around. Over here, they kind of formed a layer on your solid here, and then some of the red ones came off, and now they're floating around. It's a single. This one?
Decomposition.
This one is a decomposition. Okay. When we write our reactions in aqueous solutions, we can write them in multiple ways. The idea is to make it less complicated by ignoring the things that don't do anything, but unfortunately the end result is it makes it more complicated because there's now more than one way to write it. Okay. What we were writing with the aqueous and the solid is called the molecular equation. Just like that. With aqueous, aqueous, solid, aqueous. We also can break that up into what's called an ionic equation. When we break it into an ionic equation, we take all those aqueous ionic solutions and we break them into their ions. So here, this was silver nitrate. It broke into silver and nitrate. Sodium chloride broke into sodium and chloride. In our products, we made sodium nitrate, which is aqueous, so we break it up again. But we also made silver chloride. That's a solid. It doesn't dissolve, so it doesn't break up. So we write that combined into silver chloride. Spectator ions are every ion that is on the left and the right. So telling you that spectator ions are on both the left and the right as ions, what would you say are the spectator ions in this equation?
Silver, nitrate, sodium.
Sodium and nitrate. Sodium is there, sodium is there. Nitrate is there, nitrate is there.
Okay.
They're on both sides.
On both sides.
Yes, they have to be on both sides as the ions. The silver and the chloride are now combined into silver chloride. Did I say silver? Silver chloride is now a solid. They're on the left they're ions, on the right they're a compound. So the silver and the chloride are not spectator ions. What is the same one? Spectator ions don't do anything, so there's no reason to write them. So we can write not only the molecular equation, we can write the ionic equation where we break everything up, but we can also write the net ionic equation, where we ignore spectator ions. All we write are the things that do something. The silver ion and the chloride ion react together to form silver chloride. That is the net ionic equation. Okay. An example of a question would be, here's a reaction, a precipitation reaction. Write the molecular equation, write the ionic equation, write the net ionic equation. Okay. This one is simpler than going from Lewis dot to molecular structure like that. Here it's just a matter of taking your compounds, breaking them into ions, and then crossing out the things that are on both the left and the right. So here is our barium sulfate again. When you go, if you need to have an image done of your intestines, you drink barium sulfate. Barium sulfate is a solid, and you can see it in your intestines. So you can see this person's intestines. Okay. So we are mixing barium sulfate, we're mixing barium chloride and sodium sulfate. We have to write molecular, ionic, and net ionic equation. This is our last slide for the day. So just hang with me. You got barium chloride. Barium chloride is BaCl2. That is aqueous. We react it with sodium sulfate, Na2SO4 aqueous, to give, and it says we get barium sulfate, solid. What else are we going to make? Sodium chloride. So we've written it out now. That's aqueous. You have to balance it. So we have 2 chlorines on the left, 2 sodiums on the left. So it looks like if I just put a 2 there, it's balanced. Do you agree?
Yes.
Okay. So what type of your equation is that? Molecular. So it's a double displacement. It's a double displacement reaction. The type of the equation that we wrote is the molecular equation. The next thing is to write the ionic equation. All we have to do is break these up. So this is barium chloride is going to break into barium and chloride. So we're at barium 2 plus, because it's now an ion. It's aqueous, plus chloride, aqueous. But we got 2 of them out of here. Does everybody see that? If you take one barium chloride and break it into ions, you get 2 chloride ions. So that 2 goes there. Because you would not have Cl2 with a minus charge. That doesn't exist. Chloride ion is just Cl minus. Plus sodium aqueous, there's 2 of those. Plus sulfate ion aqueous gives barium 2 plus aqueous plus sulfate. Barium sulfate is a solid, so I do not have to break it up. So I'm going to write my barium sulfate solid plus, now I have 2 Na plus aqueous plus 2 chloride aqueous. That really long, tedious thing is our ionic equation. It's not hard, it just takes a long time to write. Now we just write our net ionic equation. To do that, we cross out anything that's on both the left and the right. Here's our chlorine, our sodium, chlorine, sodium, then you just write what's left. Barium 2 plus aqueous plus sulfate 2 minus aqueous gives barium sulfate solid. Everybody see that progression? Okay. We are done. We did not finish. So I will go home, I will look at the homework and delete the things we did not cover. Okay? Looks like the only thing we didn't cover is anything to do with energy, which there might have been one we were